Today, you may look forward to 3 exciting presentations revolving another roundup, so to speak, another meetup. The topic fluids meets solids, innovations for dosing, for solid liquid separation and drying. You may learn how to optimize your production processes with cutting-edge drying and dispersion technologies and dive into new ideas, which is always a good idea, of how to reduce costs, conserve resources, and enhance efficiency through innovative solutions. Today's talk is just another step towards autumn. Our virtual talk series will continue on a really monthly basis to address state-of-the-art issues and bring together experts from all over the places with valuable insights on process technology. And then, from September 23 to 25, trends and innovations can be experienced live, hands-on, at Powtech Technofarm 2025. Save the date. You're all welcome, and we will meet up there. And now I would like to thank our 3 speakers of today for their participation in our talk. We're very much looking forward to your speeches and insights. It is Markel Alberdi from Ekonek. It is Tim Holtkamp from Buss-SMS-Canzler and Dr. Holger Becker from Mistral. And now I would like to hand over to our first speaker, Markel from Ekonek, and his talk about pulse spray dyeing, innovative and energy-efficient powder production. So enjoy the talk, everyone, and the microphone is yours, Markel.
Well, first of all, thank you very much, Heike and Clara, for the introduction and also for organizing these virtual talks, for sure. I will share my screen, okay, so you can also see what I want to share. Let me know, please, when you can see my screen.
We see it.
Okay. On one hand, I will explain what Ekonek is as a company, and of course, I will explain what the pulse spray drying technology is. Later, we will see it more in detail, but for you to know or to have a general overview about the pulse spray drying technology, as its name says, pulse spray drying technology is a spray drying technology, but made in a different way. Okay, and thanks to this different way of spraying, we will have different benefits, mainly focused on energy efficiency. Okay. Ekonek, as you can see, well, Ekonek is an engineering company based in the north of Spain and is part of this bigger group. Okay, this group is called INSO Group and is an important group based also in the north of Spain. And as you can see, there are some companies in the machine tool industry, some companies in industrial services, some companies in digital industry of 4.0. And it's important to mention also that we have also our own R&D center in the group, which is giving R&D support to the whole group. Okay, as you can see, we are inside the circular economy group of the INSO group. And this is because spray drying technologies are also sometimes used for byproduct revalorization. Okay, in our case, of course, apart from these applications, we develop and we dry different products from different applications. Okay, but we are inside this circular economy group, inside this bigger group, industrial group in the north of Spain. Okay, more or less, we are 600 employees in the group. And if we focus only in Ekonek, we are more or less 30 people. Okay, most of us as are engineers because we don't have a workshop. So every resource is mostly dedicated to design and engineering. Okay. Our worldwide structure is the following. As you can see here, there are many different subsidiaries. These subsidiaries are not specifically from Ekonek, but they are from the whole group, in which we can also obtain support for potential projects we have in these countries. Okay. If we focus only in Ekonek, here you can see the headquarters, as I mentioned, in the north of Spain. And we also have a subsidiary in Mexico who are helping us in the projects we have in the American continent. And until now, we are focusing mostly in Europe and in America. So how do we normally approach a new customer? Okay, we know that this technology is quite innovative, even if until now we have already executed quite a lot of projects in Europe and in America. But first of all, we like to have this kind of meetings in which we first explain what the spray drying technology is. And of course, we explain why this technology has the benefits we are mentioning. Okay. Of course, we also like to understand the applications of the customers, so we can also support them in the correct direction. And normally, the second step is to perform some pilot trials in our pilot plants. Okay, we have 2 different pilot plants in Spain. The nominal capacity is 70 kgs per hour water evaporation. So this means finally that they are not lab scale pilot plants, but they are already semi-industrial. Okay. During these pilot trials, what we do is we, of course, obtain the samples of the powder samples, so the customer later can compare with their specifications, and they can compare the quality dried with their conventional dryers and with pulse spray drying technology. And apart from that, also we are recording every time all the parameters we are using during the pilot trial. So this means that at the end, we can deliver a complete report of all the parameters we used, with a complete also calculation of the energy efficiency we obtained during the trial. Okay, with both informations, both the process quality and the powder quality, they can compare everything with their current projects or the processes, and also they can compare with other technologies. Okay, this way is quite easy to obtain this comparison for a project study. Okay, they can build quite easily a business case, so they can compare everything. Of course, next step is that if we reach an agreement, we start the designing process, the building and the startup, and we close the loop with the staff training and the maintenance. Okay, so this means finally that we make tailor-made applications, tailor-made dryers, because we don't have a standard catalog. So this means that from our experience of the projects and also from our experience on the pilot trials, we make everything, we design everything according to each application. Okay. Apart from that, it's important to mention that we don't make only new or greenfield projects, but we also make retrofittings of conventional spray dryers. Okay, later we will see it more in detail, but it's an interesting topic which is also taking quite a lot of interest lately. Here we have some awards about the innovation of the technology, and let's go to the technical topic. Okay, I know that now it is not possible to interrupt the presentation, but please take notes, so later at the end we can solve all the doubts. Okay. Here in the left, you can see one of our pilot plants. Okay, and in the right, you can see the corresponding diagram. Okay. First of all, in order to differentiate the pulse spray dryers from conventional dryers, I would like to briefly explain how conventional dryers work also, or the general spray drying technology, how it works. Okay. The general spray drying technology consists in injecting a liquid to the system, and there is a phase in which this liquid is atomized, is pulverized into smaller droplets, and there is also a big amount of air, hot air, which is evaporating the water from these droplets. Okay? This is happening in this drying chamber, and once the powder is produced, so once the liquid is dried, thanks to the aspiration fan we have at the end of the system, the powder, together with the air, is going to be conveyed to the cyclone and to the back filter to be collected. Okay, the cyclone and the back filter are helping to separate the powder from the air. So these elements, drying chamber, cyclone, back filter, and aspiration fan, are common elements from spray dryers to pulse spray dryers. Okay, so what is the main difference? The main difference is this element, is the pulse generator itself. Okay, the technology, the pulse spray drying technology, is located in the pulse generator. So how we can differentiate conventional dryers from pulse spray dryers? Conventional dryers, they use a mechanical element, which is a nozzle or a rotary atomizer normally for the atomization. In our case, we don't use any mechanical element for this atomization. Okay? In our case, we use the pulses. This is why the technology is called pulse spray drying. So what are these pulses? Here you can see the 4 inputs we put into the system. Of course, the first one is the wet product. We don't need any high pressure pump like in conventional dryers because we don't have a big loss or charge in the feeding line. In our case, with a low pressure pump is enough to feed the product into the correct place, okay? Because the function of the feeding line is not the atomization, but is just to put the liquid into the correct place, okay? Apart from that, we have 3 more inputs. The first one is the gas, and we have 2 different blowers, okay? The gas can be natural gas, can be propane, can be biogas, and now we are also developing the technology to work with hydrogen. Okay, this is how we intend to electrify the technology. Apart from that, as I mentioned, we have these 2 blowers. So how do we work? We inject either air and gas into the pulse generator, and we will produce some pulses. Okay, these are some small explosions inside the pulse generator. And these pulses will deliver, on one hand, hot air, and also the shock waves coming from these pulses, okay? So these pulses, when are going down to the drying chamber, will hit the liquid which is injected from through the feeding line and will make the atomization, okay? So let's say that the main difference is that instead of using a mechanical element like a nozzle or a rotary atomizer, we use these pulses coming from the pulse generator. Okay, now we will see a little bit more in detail how this element works, okay, as it is the, let's say, the heart of the technology. The first step is that we introduce the air by the first blower to the pulse generator. This is a section, okay? And here you can see that we have a rotary valve, which is turning very fast and is opening and closing the access of this air to come to the combustion chamber, okay? In parallel, the second step is that we are introducing also the gas flow, of course, much smaller compared to the air, to the combustion chamber. And when both are together in the combustion chamber, the air and the gas, we will generate one small explosion inside. And this explosion will deliver this pulse. The pulse is the shock wave, okay? Of course, together with hot air. This is repeated more than 100 times per second. So what we will get is a stream of hot air together with pulses. So the hot air we will inject to the system is a pulsating hot air. So finally, when we inject the liquid through this injector, it's like a pipe. First, the pulses will hit the liquid, converting the liquid into smaller and smaller droplets. And of course, the hot air will evaporate the water from the droplets. Okay, so the difference from conventional spray dryers is that instead of using a mechanical element, in our case, we use this system, which is the pulse spray drying system. Okay. Until now, remember in the diagram, we will look back again. Until now, we only have seen working the hot air, the air which is introduced by the first blower. Okay. The second blower is going to be introducing air, but without being mixed with the gas, into the system concentrically to the pulses all around this darker jacket in this point. And the function of this air is just to protect the powder from the heat which is coming when the powder is already produced, so when the liquid is already dried, and also to provide the enough airflow to the system to later convey the powder to the cyclone. This happens because this secondary airflow is not heated up. Okay, we don't need any energy to heat up this secondary airflow. Okay, so let's go a little bit back to the diagram to check it again. Okay, so as I mentioned, the hot air which is going to be mixed, well, the air which is going to be mixed with the gas to produce the pulses and the hot air represents more or less the 30% of the total airflow. Okay, the secondary blower, which is the cooling air blower, is going to be injecting cold air or ambient temperature air to the system to protect the powder and to convey the powder to the cycle. So why this technology is more efficient than the conventional dryers, the conventional spray dryers? On one hand, remember that our hot air is pulsating, while in conventional spray dryers, the air is laminar, is constant. Okay. The thing is that the idea is that the pulses, let's say a pulsating hot air has a much better energy efficiency or energy thermal exchange with the liquid. So the drying process happens in much faster way. Okay. In conventional spray dryers, the drying in the drying chamber happens very slowly. So the particles, the residence time in the drying chamber is quite long. The particles are going down little by little. And in our case, almost in 1 meter, the product will be almost totally dried. Okay. This, in consequence, means that we don't need such a huge amount of air. So in our case, for evaporating the same amount of water, we use much less amount of airflow. Okay. In consequence, we need to heat up less amount of airflow. On the other hand, as I mentioned before, we only heat up one part of the air, the 30% of the air. Okay, so the efficiency of this technology comes from using much less amount of airflow for the same evaporation capacity, and also by heating up only the 30%. Okay, this is the difference on how it works compared to conventional spray dryers, and these are the reasons of the good efficiency compared to conventional spray dryers from pulse spray dryers. Okay, I will jump over some slides to continue the presentation because we will see also other additional benefits. Okay, this is a picture. The one that I'm showing now is a picture of this lowest part of the pulse generators. Okay, as you can see, this is it's a bad atomization because the injector, this is the injector, the pipe should be in the middle. You can see big particles, small particles. But if we put the injector in the correct place, later we will see that the atomization is more homogeneous. Okay? This picture is just to show that we don't use any mechanical element like nozzles or rotary atomizers for the atomization, and to show that the atomization is made by the pulses, which are coming from the pulse generator. Here, additionally, we can see the second main benefit of the pulse spray drying technologies. Okay? Normally, the spray dryers, conventional spray dryers, use these nozzles or rotary atomizers for the atomization, and these elements normally have very small holes to make the atomization. Okay? They are fed by a high pressure pump, and with this pressure and being helped with these small holes, make the atomization. This normally is quite a big limit for drying very concentrated or very viscous products, because these small holes, if we inject very concentrated products, can be quite easily clogged. Okay. In our case, as you can see, our injector's diameter is much bigger. Imagine that, like in industrial projects, this diameter can be even 1 centimeter diameter. So this finally means that we can feed much more viscous products, much more concentrated products, and even with some solids in suspension. Okay, so this benefit, on one hand, is good for drying complicated products, like with solids in suspension or very viscous products. But on the other hand, also, if in previous processes, the process is able to concentrate the feed more, then we are injecting less water to the system. So we need to evaporate less water. Okay, so on one hand, the evaporation is much more efficient. But on the other hand, if we can benefit with this second benefit, of course, we can improve or optimize much more the global OPEX of the process. Okay, because we need to evaporate less water from the product to obtain the powder. If we put the injector in the correct place, this is what we get. Okay, as I mentioned, in conventional spray dryers, normally the air is going down little by little with the particles. In our case, as we don't need such a long residence time, the air is going directly down to the cone. Okay, as you can see, we have different types of injectors, external, internal. We have developed more than 20 different types of injectors, and this is helping also us to reach the correct specifications on particle size distribution. Okay, of course, we know that the particle size distribution is an important topic for different companies. So we have different parameters to adjust, and we are able to be flexible also in this parameter. Okay, we can play, for example, by choosing the correct injector, we can play with the concentration of the feed. So if we adjust all these parameters, we can reach the specifications on particle size distribution. Generally, apart from that, what we have seen until now, and also our customers, is that the particle size distribution graphic we obtain from drying is more flatter. Okay? Let's say that the particle size distribution we can obtain compared to nozzles or rotary atomizers, in our case, is more homogeneous, okay? Which is normally a good point for having a standard product, okay? So just to give a small summary of the main benefits of the technology, we have seen the differences from conventional spray dryers. We have seen the reasons of these benefits. So in order to have a small summary, the first one is the last benefit I mentioned, and is the possibility of atomizing and drying much more viscous or much more concentrated products, even with some solids in suspension. And remember that this is an important topic because with this kind of products, normally the conventional spray dryers are limited. The second reason is that thanks to the fact that we evaporate the same amount of water by using less amount of air, and we only need to heat up the 30% of the air, then the running costs are also lower, 20 to 30% on average, but in some applications we have also lower up to 40%. The third point is that as we are not using high pressure pumps, we are not using nozzles or atomizers. Normally these elements need quite a lot of maintenance. In our case, we reduce also the maintenance costs. Of course, the pulse generators need also some maintenance, but we don't need to remove and we don't need to exchange the whole pulse generator. Okay, we normally make a preventive maintenance of the pulse generators by changing some small pieces of the pulse generator. Okay, and finally, as a last benefit, but of course important, these three benefits wouldn't make any sense if the final product quality is not high. Okay, so until now, from the pilot trials we have made, also from our customers and also from other third-party certification companies, we have checked that the product quality is similar or the same as conventional spray dryers in general basis, but of course, it has also other benefits which are much more specific for each market. Okay, so let's say that these are the main benefits compared to conventional spray dryers. Okay. Regarding applications, let's say that all the applications that can be dried with a conventional spray dryer can be dried also with a pulse spray dryer technology. As you can see, our main applications are food and feed, with flavors, with aromas, with plant-based products and proteins, also byproducts. We are focusing also a lot now in ceramic minerals and chemicals because we see that these benefits can be applied very easily. And apart from that also, we have made different applications regarding fertilizers. Okay, so let's say that we have a broad different applications in which we can apply the pulse spray drying technology. Okay, if we move forward a little bit to see some applications or some references, here you can see some pictures again of our pilot plant. Is the 70 kg per hour water evaporation, and is where we develop each product and each application with our customers. And of course, we also work on making the technology even more efficient and even more flexible on R&D basis. Okay, so let's say it's a pilot plant for our customers for developing the products and for validating the processes, but also is the one that we use for improving the technology itself. Okay, here we have another, let's say another reference. In this case, is evaporating 1 ton per hour water evaporation. Okay, this is the first industrial reference we made. It was made in 2016. Okay, so the company started in 2009 until the 2016. The work that it was done in Ekonek was only R&D, okay? Only development, and the first industrial project was in 2016. It's important to mention that this is the first industrial project, but is working almost non-stop during the whole year without any problem. Okay. Here you can see some pictures. Here we have another reference, which is also 1 ton per hour water evaporation for drying hydrolyzed protein. And here we have also another important topic compared to conventional spray dryers. Okay. I mentioned that the total evaporation capacity of the dryer is 1 ton per hour. Okay, but this 1 ton per hour is divided into three different pulse generators. Okay, so this means that the 1 ton per hour is reached by the 350 kgs per hour, which are evaporated from each pulse generator. Here you can see the gas trains for each pulse generator, and here you can see also the air inputs for each pulse generator. So this means that it is a modular, let's say the capacity is modularly increased. So this means that it is also very flexible in terms of productivity. In some companies or in some applications in which there are some seasonalities during the year, or there are some different production peaks and valleys in the production, then we can switch on and off each pulse generator to reach the specific evaporation capacity we want. Okay, so let's say that is also very flexible in terms of evaporation capacity. And just to finish a little bit, I mentioned in the beginning that apart from making new dryers, so greenfield projects, we are also retrofitting existing dryers. Okay, and this is also an interesting topic because many companies have many different conventional spray dryers, and they are looking for optimizing these processes. So in this case, it's not necessary to exchange all the dryer, but only make some small modifications so we can obtain the benefits of this technology. So let's explain more or less how this works. Okay, what we propose is to keep the drying chamber, cyclone, back filter, what is downstream from the technology itself, from the pulse generators, and we propose to remove the top part of the drying chamber and to put one or several pulse generators with the blowers and so on, and also new feeding lines to the dryer. So in this way, we will keep almost all the elements which are installed, and we will put the technology, which is the pulse spray drying technology, inside the drying chamber by keeping the rest. Okay, so with this kind of retrofits, we can make three different benefits. The first two are because of using this technology. One is that we will reduce the energy consumption. The second one, of course, is the possibility for spray drying or for processing much more concentrated products. And the third one is that we can increase the evaporation capacity of the existing dryers. So we can increase the production of the existing dryer. Okay, why does this happen? I mentioned at the beginning that for evaporating the same amount of water, we normally use a smaller amount of airflow. Okay, so the consequence of this is that if we are going to design a dryer from the beginning, our dryers, let's say our drying chambers, are smaller compared to conventional spray dryers for the same capacity. Okay, so if we already have a drying chamber which is coming from a conventional spray dryers, this normally is bigger than what we need for the evaporation capacity, and what we can do is to increase the evaporation capacity of this existing spray dryer. Okay, so finally, it's a good solution either to make an optimization on OPEX, but it is also a good solution to increase the evaporation capacity. Each dryer cannot be, the evaporation capacity cannot be increased in the same way, but on average, we are able to increase on 20 to 30% the evaporation capacity. Okay, so let's say that this is what I wanted to explain. On one hand, what is the pulse spray drying and what are the main differences from conventional dryers? What are the benefits and why? So the reasons of this efficiency and these benefits, and what type of solutions we are having. Okay, so let's say that this was everything I wanted to share today. So of course, if there are any questions, I will be happy to answer.
Perfect. So thank you very much, Markel. So as he said, if you have any questions, please feel free to use the F&A button at the bottom of your screen, and there you can type in your questions. Or when you're joining over LinkedIn, please feel free to ask the questions over the comment section. And I see we have the first question. So first of all, the person thanks you for the presentation. And is this technology suitable for drying peptides?
Well, in our case, in my case, I'm working in Ekonek since 2 years ago, and I know that some peptides have been dried by the pulse spray drying technology. But to be honest, I cannot answer to that question right now because I have not this experience on the historic period of the Ekonek, and I cannot make any specification on that. But I know that these peptides have been dried with any problem with pulse spray drying technology.
Perfect. Thank you for answering. Then I will ask you another question. So would it be possible to try heat-sensitive products?
Yeah, this is a good question because, of course, here as we have these explosions for providing the hot air, normally this is a typical question, okay? Because the heat which is produced is quite high. But in our case, we have different references for food applications which are also very heat sensitive. So the good point is that we can apply the different parameters to the drying process regarding temperatures, regarding airflows. So by applying the good parameters on the drying process, we can dry without any problem heat-sensitive products. Okay, we have a reference for giving an example, drying a probiotic, which is a fungus, which is very, very heat sensitive, and we are drying it without any problem. So let's say that is a matter of adjusting the parameters correctly.
Perfect, thank you. So we got a few more questions. Is there a total solid content limit to the feed material to the PSD? And is there a general viscosity limit to the feed to the PSD?
Yeah, this is also a good question because it's one of the main benefits of the pulse spray drying technology. The thing is that the solid content, it depends on in what product we are talking about, because of course there are products that with very few solid content, they are very viscous, and there are products that even in 80% of solid content is not so viscous that we can also dry. But the second question is the good point, and the reference we have, for example, and from our experience, is that we have been able to dry products above 20,000 centipoas. Okay, so depending on what product, these 20,000 centipoas can be reached with less or more solid content. Okay, but regarding this topic, the solid content is not the only parameter playing on the viscosity. So there are also other different parameters like surface tension and other different ones that can be also playing a role in that.
Perfect. I see we have another question. So is there any information about the droplet size distribution?
This also depends a lot on what product is going to be processed and in which percentage of solid content. Okay, let's say that the viscosity is playing a role here and also the concentration. So depending on how viscous this product is or how concentrated this product is, the droplet size, so in consequence, the particle size will also be a consequence. Okay, so there is not a single answer for this question. We should look more specifically for each product to determine what particle size and what droplet size we can get.
Okay, I hope this question is answered. So, and how is the particle size distribution controlled?
Yeah, here I mentioned a little bit, but the particle size distribution in our case can be controlled in a few ways. Okay, the first one is by using different kind of injectors. I mentioned injectors like a pipe, but they are quite more sophisticated than just a pipe. So by choosing the correct injector, we can adapt the particle size distribution. This is one topic. And the other one topic, the other main topic is that we can also play in the concentration of the feed. So we can concentrate more the product to get bigger particle size. And if we need a smaller particle size, we can dilute it a little bit. So we have different parameters to play with to reach this specification.
Okay. And are you able to produce the pulsation in any other way? For example, if you want to use an electrical energy source.
Yeah, in our case, for these pulsations, we need a gas. Okay, we need a combustion. So we need one gas. Now is natural gas or biogas or propane, for example. But as I mentioned, we are also developing the system already to work with hydrogen. But the question or the answer for this is that just with electricity, we cannot produce these pulses nowadays.
Okay, thank you. I think the last two questions. If inlet product is more concentrated and time residence shorter, is that correct to say the drying chamber will be smaller for the equivalent production of dry powder?
Yes, that's true. Let's say that if we are using less amount of air for the same evaporation capacity, as the residence time will be smaller, the drying chamber we need is smaller. So finally, the total layout of the dryer, and also the dimensions of the drying chamber are smaller compared to conventional spray dryers. That's true.
Okay, perfect. And what is the life expectancy of a pulse generator?
Well, until now, I mentioned that the first industrial project, was in 2016. So these pulse generators with a good preventive maintenance, they are still working without any problem. So let's say the preventive maintenance consists in planning this preventive maintenance and checking some pieces which are part of the pulse generator, and we exchange them whenever is needed. Okay, but it's not the pulse generator itself, but only some pieces. And in this case, these pulse generators are not showing any problems since 2016, and the expectation is to keep these pulse generators for a long time.
Interesting. Thank you for answering that. And then I think we can answer the one last question. So then we were running a little bit out of time. So last question, how comparable is the total energy consumption of this technology compared to the conventional spray drying technology, as you need here energy for combustion?
Yeah, here on average, let's say on average, for evaporation, on average, the pulse spray drying technology is 20 to 30% more efficient than conventional spray dryers. This is just for evaporation. If we add the benefit of spray drying more concentrated products, we would be injecting less water to the system. So we can combine both benefits to have a global OPEX even more efficient. Okay? But if we focus only on evaporation, the energy efficiency is 20 to 30% on average better than conventional spray dryers, even though we have been reducing this number up to 40 in some applications.
Okay, perfect. I think you have answered all the questions everyone had. So then thank you also for your very interesting presentation and for your talk. And then I will hand over now to Tim Holtkamp from Buss-SMS.
Thank you very much.
Yeah, thank you. Right, we continue with Tim Holtkamp from Buss-SMS-Canzler and his talk about efficient drying solutions, saving energy with contact dryers. I'm very excited. So, Tim, the stage is yours.
Thank you very much. Can you hear me?
Yes,
Everything
we hear
good?
you.
Okay, perfect. Yes, thanks, Markel, for the presentation. It was very interesting. And thank you for being here today. I will try to share my screen right now. Please give me a sign when you see it.
We see it. Thank you.
Okay, perfect. Yes, I've been working in my company, Buss-SMS-Canzler, for 6.5 years now, and we are a supplier that is already over 100 years old, and we supply tailor-made process equipment, and we provide, in my eyes, very interesting drying solutions by the use of so-called contact dryers. Our head office is located in the center of Germany, close to Frankfurt. There we also have our fabrications. We have a small branch office close to Cologne in Düren. There we have some engineering activities. One small office in Erlangen in Bavaria, where we perform CFD and DEM simulations, as well a place in Switzerland close to Basel and Bratteln. That's where I'm located, where we have our process development. And there we have our own laboratories where we can perform laboratory trials with our customers. We have even bigger metal pilot plants where we perform pilot trials for scale up and further feasibility. And also, in addition to that, a partner lab where we can make analysis. And as I said, CFD and DEM simulation for accompanying analysis. We are also active in the process equipment for evaporation technology with our thin film evaporators and with equipment for the treatment or processing of polymers. But today we look at this drying technology, which is called contact dryer. So because I think that just a few people will know this technology, we will first of all have a look on the physics of this technology. Most of you probably know the kind of dryers that you see here on the right side, and also this kind that just Markel Alberdi from Ekonek has just presented to us, which is the so-called convection dryer. So a dryer that you all know also from everyday's life, when you come out of the shower with your wet hair and then you take your hair dryer and blow hot air over your hair, and then the hot air will saturate with water and the hair becomes drier, and then the wet hot air leaves this system. Yeah. So this is a classical convection or convective dryer. On the other side here, on the left side, you see our drying systems. We call them contact or conductive dryers. They do not use air at all, so we don't have an inert gas here. What we have is the product, the wet product that is brought in contact, in very close contact to a heated wall, for example, a double-jacketed machine with a thermal oil in it or steam in it, and the heat will be transferred through the wall by conduction into the product. The product heats up, and then the water, for example, starts to evaporate, and inside the dryer we just have pure vapors and nothing else. So, but this, supposedly small difference has really far-reaching consequences. Yeah, and I will explain to you these consequences later. Just to give you an impression how a setup can look like with a contact dryer, we have here, for example, a thin film dryer, which is a cylindrical machine with a double jacket where the thermal oil, for example, is circulating. We have a feed nozzle where the wet product is pumped in. We have an agitator that presses the wet material against the heated wall and then pushes it down slowly where it's being dried, and then it leaves in the bottom, and the vapors go counter currently in the other directions, and they can be externally condensed. One, let's say, level of abstraction higher, we can summarize this picture here as a general, very easy setup for contact drying. So the contact dryer in the center, a heating unit besides, a feed system, an outlet system, and an exhaust nozzle. On the right side, you see a comparative system with a convection dryer. There you see this green flow, which is one more and very big flow. This is the flow of air, yeah, that in the previous presentation was talked about a lot. Yeah, this could be reduced a lot in this pulse spray dryer. But here, so in our drying systems, we don't have this, yeah, which make the systems much more easy, simpler, less complex. In both cases, you can try to recover energy. In our case, we can recover the latent heat completely, nearly completely, and also we have the full recycle of the solvent that we have just evaporated. This is only partially possible with convective dryers. So, and then I've looked into literature and I found the Bible of drying technology. Here you can see it from K. Gröll, Trocknungstechnik, 2nd edition, page 536. I found the complete energy balance. You can see here the streams for a convective drying system. And then I took these values and I simulated the same for a contact dryer to have a comparison between these two worlds. And what I figured out is that the energy consumption in the convective dryer is approximately 14% higher, which is actually not so much than I expected, but it's still there, this difference. Actually, the thermodynamic limit would be 0.64 kilowatt hours per kilogram of evaporated water, which is corresponding to the pure evaporation enthalpy. So the net energy consumption, including the very good energy recovery we can achieve in our dryers, is 475% more in convective dryers. That's because we can only recover approximately 60% less in the convective dryers than in our drying systems. And also very interesting, what is the temperature of recovery? We can recover the energy in a condenser that you can see here, at nearly the boiling point if we use, for example, a mixing condenser, whereas to condense the water from the airstream that leaves the machine or the dryer, the convective dryer, can only be recovered at very low temperatures, which makes this energy pretty useless in my eyes, but this can be discussed. In addition, we have this big stream of 1,700 cubic meters per hour of air, which is not present with our dryers. So how can we recover this energy? The big question of energy recovery. We can implement our dryers in many ways. First of all, the vapors can be directly used. They have 100 degrees boiling point of water at atmospheric pressure, for example. So you can condense them anywhere, or you can condense them in a mixing condenser and then use, for example, 95 degrees Celsius hot water to preheat something somewhere else in your plant. But what I also wanted to tell you, which I think is very interesting, what is future, because it can help you to electrify your process, is that you use a heat pump. For example, here on the left side, you can see an open loop heat pump, or we call it mechanical vapor recompression. So you use the steam that comes out of the machine, maybe just part of it, and then you compress it with a fan or blower to a higher pressure level, for example, to 160 degrees. And then you can use it self-sufficiently to heat your own dryer. We have not yet done that actually, but I'm very open to talk with you about that. If you have possibilities or if you want to go this way, we are very open to go one step further into this future. But you can also use, if you want, a closed cycle heat pump, the classical heat pumps that you know from your homes, where your vapors are condensed inside the heat pump, and then in a secondary circuit you can use the pumped up heat for your own dryer or for somewhere else. So I've found out or figured out 2 rules of thumb that can be applied when you want to validate the use of self-sufficient heat pump system. I would say they pay off faster the smaller the dry matter amount is in your mixture that you feed into the dryer, and the further below 1 the ratio of price per kilowatt hour of electric to fossil energy is, including CO2 taxes divided by the COP of the heat pump. That's so complicated. That's why I fear the formula. Just divide the price for electric energy by the price of fossil energy. For example, this can be 2. And then you divide by the COP, this is the coefficient of performance of the heat pump, which, for example, in case of this value to be 2, this whole ratio gives 1. This would be the critical point where you say, okay, this doesn't make sense. But if the COP is bigger, and that's very probable, then we are below 1, and then you can really look deeper into this topic. To summarize, our machines or our dryers are a little bit like a distillation plant, like an evaporation. So for us, it's very easy to have a vacuum process to lower the boiling point, to lower or to make the process more gentle. We don't have oxidative stress because we don't have air inside our system. So this makes the system pretty simple, pretty compact. The energy consumption is very good. Energy recovery is high at a high level of temperature. material recovery, so closed solvent circuit is nearly 100%, so that we can meet ATEX requirements or really toxic solvents or whatever is inside your product. Yeah. Some neutral points, I would say. Sometimes we have problems with crust forming products. Yeah, here I think convective dryers are much better. Yeah, but we have also invented a very, very good solution to meet this problem, which I will show to you later. And in its very basic configuration, I think a convection dryer is a little bit more gentle with regard to the product temperature. So let's come to our dryers and the application of our dryers. We can feed into our dryers actually anything, everything you can imagine. So we can feed solutions, light solutions or dispersions that are completely liquid. We can feed liquid but pumpable slurries, no problem. Yeah. But the critical things are then the pasty sludges. We can also, without any problem, feed them into our dryers, and they are then further dried, but also wet powders. And then what you get out from our dryers are in the end powders or granules. But unfortunately, we don't have really the control over the size and distribution of the particle size that we always say it happens as it comes in the end. So let's now see how our dryers look like. Have a look in our SMS dryer family. We can distinguish two kinds of dryers. On the left-hand side here, our low hold-up thin film dryers. Yeah, we have a vertical one, the CP dryer, and the horizontal one, the D dryer. Please, for questions and answers, I don't know why they are called CP or D dryers. I have no idea. And on the other hand, we have the large volume dryers. And here I will just show to you our CFT dryer. The vertical and the horizontal thin film dryers, they have very short residence time and the plug flow-like behavior. So residence time inside the dryers is really either a couple of seconds or just a few minutes really. And on the other hand, the CFT dryer is a backmixed dryer, so no plug flow-like behavior. Here we have residence times that exceed some hours. Let's have a look at the low hold-up dryers, the thin film dryers. You can see here in the background a picture of the rotor of our vertical CP dryer. It's characterized by a flap rotor or pendulum rotor, as we call it. This CP dryer is very good for crystallization, for salt solution evaporation with sudden phase transitions. And we can feed into this machine liquid to light slurries. On the other hand, we have our general universal weapon, our horizontal D dryer. This can be fed with everything that is also liquid, but mainly pasty and dry powder, wet powder. The setup of here, in this case, a horizontal D dryer is a classical distillation setup. You have the horizontal dryer with a double jacket, heating medium inlet and outlet. We have the feed can be realized with an eccentrical screw pump or a twin screw or a single screw, and the product will be fed into the dryer. The rotor takes it up and then pushes it to the right, and then it will be dried and falls out of the dryer with a rotary valve or a gate valve. Counter currently, the vapors will leave the machine, for example, through a dust filter, and then the vapors can be 100% condensed in a condenser. The same is true for the vertical machine, but just that the machine is vertical, so feed goes in the top and leaves dry in the bottom. The working principle of a thin film dryer is actually pretty simple because the name already says you that the rotor inside the dryer will form a thin film on the double jacketed internal of the shell, and then the heat will penetrate the metal, penetrate the product. We have here a remixing situation in front of the rotor blades, and then the product will heat up and start to evaporate. The horizontal dryer has rigid elements or rigid rotor blades, whereas the vertical machine has pendulum rotor blades, which are very good for hitting crusts away. The temperature profile of your product inside the dryers, the thin film dryers, is very similar. So here we have the dryer axis in black, feed inlet, dry product outlet, and here the temperature axis. Here on the right side in red, we have the temperature of the thermal oil or of the steam on the heating side. And then in blue, the product that comes in maybe at room temperature, then it heats up, heats up, heats up until we reach the boiling point, in this case, maybe of water, of any solvent. And then we enter into the first drying section, which is the superficial drying of your solvent. So in the drying section, we evaporate relatively temperature neutral, and then we reach a critical point. This is the phase transition, where we have the transition from liquid to solid. There we go through a very viscous, sticky phase, and then the horizontal dryer and the vertical dryer take different ways. It's clear that when we are solid, that the product in the vertical machine will not stick to the wall anymore. It will just fall down and leave the process. So then the drying is over. But in the horizontal machine, we still remain in the dryer and feed further up and enter into the second drying section, where we try to evaporate the capillary bound moisture or solvent. So this region here is mainly dominated by diffusion. Let's now go to the other class of large volume of contact dryers, which is the large volume dryer. We call it CFT dryer. That's very good for crust forming products, liquids or slurry feeds. We have a direct phase transition inside the dryer. Granulation is possible here, and it's also ideal for poisonous waste streams. Here you can see a picture of the internals of the pedals of this dryer. It's actually not so easy to understand how this dryer works, but I always say that it is a mixture between a fluidized bed dryer and a contact dryer. Contact dryer because there is no air inside, and fluidized bed dryer is because you can see here a DEM simulation. The paddles create a fluidized bed in the bottom of this partially filled machine. So, but how does this work? So we have exactly like with the other dryers, a double jacketed cylindrical machine. We have a rotor inside that moves, in this case, the pre-fill, so the bed that is already inside the machine. And then we have inlet nozzles that feed directly in this hot bed. And in the moment that the wet product reaches this bed, it will directly evaporate in situ in this hot, very hot bed. The bed locally will cool down a little bit to provide the evaporation enthalpy, and then everything around is dry. So this means before the sticky phase transition area touches or can touch the wall, it is already dried. This is why this kind of dryer is used for really crust forming products. The temperature profile in this backmix dryer is, as you can see here, so we have the dryer axis here in black again, and we have the temperature axis here in blue. The heating temperature is uniformly over the whole length of the dryer, approximately 18 to 100 Kelvin above the boiling point of the product that you want to evaporate. And the bed temperature is somewhere in between. Yeah, and there where you can see the nozzle, these little slopes here, there is the inlet nozzle of the wet material. So there we have a little temperature sink, and the lower the feed rate is into your dryer, the higher the bed temperature with its maximum, that the bed temperature is the same as the heating temperature, and the higher the feed rate, the colder the bed will become up to a critical point. This is what I call the bed collapsing point. That's when the bed is getting too cold and it will collapse, so there is no fluidized bed anymore. The setup of The setup of this dryer is also a classical distillation setup, with the difference that the feed nozzles are here evenly distributed on the top and over the whole length of the dryer. And since it's a back mixed dryer, we have on the right side here a calming zone where this fluidized bed starts to calm down a little bit, and a wear over which the solid particles that are really already bone dry will then exit the machine, and they are discharged via a rotary valve or a gate valve. So that is our sales team and some of our representatives. And I thank you very much for now for listening to me and for your interest. I hope you have some questions.
Yes, right. Thank you very much, Tim, for the interesting presentation. As you said, you can now ask your questions over the F&A button at the bottom of your screen. So please feel free to ask your questions. And also everyone who is now joining on LinkedIn, please feel free to ask your questions in the commenter section, so then I can also forward it to our speaker, Tim. So I will wait a few moments that you have time to type in your question. And maybe for now, one general questions from me. Into what countries do you export your machines?
Actually, over the years that our company has been existing, we have developed a really broad network, so we deliver everywhere except for the sanctioned countries. So right now, I think not Russia and not, I don't know, Venezuela or something like that, but normally all over the world.
Okay, perfect. Thank you.
And we also have our service, everywhere in the world. So this is not a problem.
Okay. And one question is coming in over the F&A button. What about the saving energy by vacuum operation?
Yeah, vacuum operation is an interesting topic here because our dryers work with the principle of evaporation, like a distillation, which means we have to always preheat our material to its boiling point. So if we suck vacuum, then this boiling point is lower. So for example, I don't know, 100 degrees water boiling point at atmospheric pressure. Under vacuum, we can have a lower boiling point, which means that the preheating energy input is not needed anymore. Yeah, for example, because we evaporate at 40 degrees.
Okay, thank you. Hope this question is answered. And another question: if you have excluded the reactor term from your presentation, is there a reason for this?
There's not. It's actually a little bit too long for the presentation, and we don't use this too much as a drying device. It can be used for this, but it is also used for like a simultaneous drying and reaction. That's because it's named reactor term. So in the end, it's a kneader. We can imagine to perform chemical reactions in there where dry material can go out in the end. Also, the treatment of pyrolysis residues and so on are possible, but that's an own chapter. That's why I've not included this into the presentation.
Okay, thank you. So we have another questions over the F&A button. Have you looked into steam recompression coming out of a dryer operated at vacuum pressure?
I don't know if I understand this question. So I think I try to understand it. So vapor recompression in combination with vacuum inside the dryer means, how about we use our dryer under vacuum, we operate it under vacuum, and instead of condensing the upcoming streams in a condenser, we directly let the steam go through the vacuum pump and compress it then. So, and what is the question now?
So the question was if you have looked into steam recompression coming out of a dryer operated at vacuum pressure. But if the question is not answered now, it's also okay that the asking person can also maybe find out what's the actual question is.
So
And
the thing is, in the end, steam recompression needs, if you are under vacuum, the density is pretty low of the steam. Yeah, so this can be maybe a little bit difficult, but it's possible. Yeah, the blower
okay.
needs to be very big due to the low density of the steam in the
Okay.
vacuum.
Perfect. So thank you for for answering this question. And the last question, I think, is it possible to selectively condensate the solvent when it is a mixture solvent?
Yes, absolutely. You can treat our systems as any kind of abnormal standard evaporation. So you evaporate in our dryer a solvent mixture. We often have this case actually. And then you can recondense this in a column directly on top of our dryer, yeah, with a partial condensation, for example, in the top. And then you have a washing column and you can directly separate or split this mixture in this column. This is possible, yeah.
Okay, perfect. So I think when no questions are left, thank you very much for your presentation. If some questions are not answered now, please feel free to ask the questions to powertech-technofarm@nürnbergmesse.de. We will forward it, or ask Tim Holtkamp directly the question. So thank you very much, Tim, for your interesting presentation.
You're welcome. Thank you.
Thank you. So now, last but not least, we start with our final talk. The topic is dispersing systems, how to avoid common source of error in process plants. So thank you, Dr. Holger Becker from Justral, for the presentation. I'm very excited about it, and I think the stage is yours.
Yes, thank you very much for the nice introduction. Let me share my screen. So, one moment. So, perfect. So, yeah, I want to talk about the maximum efficiency for success factors if you want to integrate a dispersion system in your factory or in your setup in general. Yeah, first a brief overview of our company. And then I want to talk about the mix and dispersing systems, and then I want to show you some concepts. And what is really interesting then the daily challenges that we talk about and what we have also with our machines. Yeah, at first, Östral is located in the really southwest corner of Germany in the beautiful Black Forest, but we're working around all over the world. So we have also different distribution centers, and are also located in India and Singapore and Bangalore, for example. And yeah, our products are handle all equipment for mixing of liquids or solids into liquids. So we have a jet stream mixer, we have dispersion units, and we have also the inline dispersion and the powder wetting machine, which is called Conti TDS. To this machine I come later. I will talk later a little bit. But in general, Östral is also for process engineering. We've tried to find the perfect solution for every customer. So we can handle from just the machine and up to a complete system. And we can build on modular systems, like you see here. So we have on the one side, we have the liquid side, and on the other side, we have this powder handling also. And that overall, we have a control system, which can be very easy or very complex. It depends on the tasks of the customer. Yeah, and Östral machines are involved in nearly every product, from chemistry to pharmaceutical industry, the food industry. So you can find it everywhere. For example, if I take this energy drink, we are also inside the energy drink, as by producing it, and also the glue between the top and the bottle, and also for the color industry, for the paint industry. Yeah, what we are doing, this is how often powders are handled. You put them in the top of a vessel, and then they just start stirring, and then like you see here, you have often the problems that it stick to the wall, it's on the surface of the liquid, and the mixing is very difficult. And also, what also a lot of people know is when you want to produce a wallpaper glue, for example, or a binder solution, and you are working with and dissolver technology, you see you have a lot of agglomerates which are in the liquid, and it take a lot of time. But if you wet your powder under our machine, for example, the powder wetting machine, you see you have the same result, but a really clear solution, and that's after 3 minutes of the powder induction. What we can't influence is the solving time itself, but what we can do is we can wet the powder very fast and create a high surface and then high dispersion inside the system. How we do that? We do that with like it's called a conti-TDS. It's the principle of an inline dispersion machine. You have a rotor stator system inside, and this rotor stator system accelerates a liquid in a circle. And in this circle, you have at the first point a vacuum, and in this vacuum, you can suck in your powders. And these powders will be dispersed to the machine. How do it look inside? If you take a look inside the machine, you see here we come from the front side with our powder. It will sucked in the machine, and then you have here the rotor. The rotor is inside and outside of the stator. And now I show you some pictures of what happens to the powder in detail. At first, we suck in your powder. You have your agglomerates like you see here. The powder it sees at first the vacuum inside the machine, and this will create distance between each of the particles, because we suck out the air, we have a vacuum, so we have more surface of the powder. The same happens to the liquid. The liquid is also accelerate in the vacuum a little bit, and then you have a high surface of liquid and solid. And in this time, it's now here between the rotor and the stator. We come together, liquid and solid. You put in your liquid, and then you have a shearing of your agglomerate, and this will crack your agglomerates. And at the end, you have a fine dispersion of your solid into your liquid. How we can do that and which sizes are typical for these machines? We can start with an R&D machine. Like here, see a calcium carbonate or Schalk suction. So we suck in with the smallest machine of around about 20 kilograms per minute, and the liquid will be accelerated in the machine around about 15 cubic meters per hour. And this is typical for R&D. That means we have a volume roundabout from 10 to 100 liters. If you go a little bit to the industrial scale, you have the size 3 of the conti-TDS. This is, for example, for Schalk, you have now 200 kilograms per minute of the suction rate. And yeah, you see here, and these typical sizes are so round about 500 liters up to 2000 liters. And if you have really high throughput, or you need a really high throughput, and then you can go up to the size 5, and then you have suck in of 600 kilograms per minute of Schalk, for example. And you see here are some other examples of powders we are typically handle. And you see if like fluffy powders like aerosol, of course, the suction rate is related to the bulk density and also to the flowability of the powder, and then it's a little bit lower. But overall, it's very fast and a high efficiency for powder wetting. So how we can now have some concepts how you can install the machines in a typical setup. And now you see here that's an ideal installation of a conti-TDS and a jet stream mixer. It's in a circle. You have a liquid inside, the liquid outside, and the liquid comes from the backside. The powder comes from the front. They meet in the mid of the chamber and will be pushed again back to the process tank or the process vessel. in ideal cases, you have normally you have a valve before and after the chamber. What is also important is that you think about the product viscosity. If you, for example, work with low viscosities, you can use this setup. Low viscosity means up to 10,000 amperes at a shear rate of 10 reciprocal seconds. And if you have higher viscosities, then you have to work with additional pumps in the system to be sure that you have the right flow rate inside the chamber of the Conti TDS. What is also important is that you have a vertical mixing in the tanks. That means no centrifuge effect inside. So that means that if you have it work with a normal mixer, it would have like something like a centrifuge. It means the heavy particles on the bottom and the light will on the top, and you only stir in a circle. With a vertical mixing, that would be an ideal case. Yeah, that is now, you see here, like I shown, the easiest setup. Yeah, some process of the powder side, you can think about big bag stations, you can have a powder hopper, you have silos, something else what you can imagine. Just important that you have a short way, in an ideal world, you have a short way for the powder, and you can accelerate the liquid in a short circle. Now you see here's also a thing for a semi-batch production or a semi-continuous production. You can work with a double tank system. And now you see here for the paint industry, you have a complete setup of starting with the Conti TDS, you have a one process tank. You can pump in your liquids in the system, and then you have the different ways for the powder from big bag station, and here like a sack handling station, for example. This is now for the pharmaceutical industry. It's a really compact system, but it's in general, you have, again, you have a short circle for the liquid handling. You have the digestion mixer inside. You have a control station close to the system. And here, if you have special powders, for example, you have a containment system you can work with. And for example, you can pump in, or over a vacuum, you pump in your powder via vacuum. You can suck in your powders here, and from here you suck it, that's your powders inside the machine. Yeah, for example, if you compare now the Conti TDS with the classical dissolver technology, you have a better energy density. You have the shear gradient is 1,000 times smaller, but you have the same efficiency. That is very important. Sorry, 10,000 times higher, but the higher shear rate. And also higher outputs when you compare. The advantage is that the machine is not related to the process tank. So all the magic happens inside the chamber, and how big your process tank is doesn't matter. It's just a factor of time what you need to have a circle, to generate a complete circle. And you think about 40 cubic meters per hour, and you have a 40 cubic meter tanks. That means it takes 1 hour to have to fulfill one cycle. It's only one thing. But then again, the suck-in time is every time the same. Doesn't matter how large your tank is for the amount of powder. So can you choose your production cost, the production time, and also the energy can be decreased in overall. Yeah, if you now think about the daily challenges, what has happened often and what we see or I see often is at the customer side is when you think about you have a powder, you have foam formation, the powder will be not sucked in, you have too much powder in the chamber, there's sometimes blockage in the pipes, your vacuum breaks and make like something stop suction. And also challenge is what is about the temperature and the vapor point of the liquid, which didn't take take a look into account, and also have pressure loss due to your piping system. That means pipe diameters are not correctly. You have unfavorable T-pieces that I will tell you in a few slides. And sometimes also what not take into account is the viscosity changes during the production. And also often as a topic is the pipe length for the machine. And so in general, you see, if you're, like I said, if you work with a normal mixer, you have also corners inside your process tank which are not mixed. And what is also possible is a shortcut. If we hand it over to our system, that means if I would remove the jet stream mixer, then I have just a circular pump that would be maybe mixed your tank also. But we have, for example, with a normal machine, we have around about 40 to 50 cubic meters per hour. That means that it's so fast that we create a shortcut inside our process tank, so that the top corner, for example, will not be mixed. And we have here a flow of high concentrated product stream with your powder inside. And if I think about exothermic reactions, that would be a terrible thing. And also for something like for binders or for xanthan, something like that, it would be too thick to pump it, and then you will block the machine, and that would be a horrible case. So that's the reason why we need a vertical mixing during the whole time and to have a homogeneous solution. So now we have one for titanium dioxide and then polyol, or for example, what we delivered was in quantity DS5 with a big bag station. And then I get a call from the customer, and he told me, now I have liquid in the powder on the powder side. And then I say, we have to take a look. Then I check, okay, we have a large process tank with round about, I think it was 25 cubic meters. We have an DN150 pipe, which was reduced to DN100. This is on the back side of the tank. That is perfect. This is really fine for quantity DS5, so you have to work with DN100. So that is not a problem. But then I take a look on the liquid on the inside, how the liquid comes to the quantity DS. You see here we have an unfavorable T-piece, and what we also have is a filter. And these 2 points together creates a pressure loss. That means the quantity DS, which controls itself during the powder induction. That means normally the machine brings away more liquid than it gets in, and it's control itself, so it's really easy for the customer to use. But in this case, the machine didn't get enough liquid. So that means we create a vacuum from time to time in the chamber. And that was a result that when the vacuum breaks, we have the liquid would be pushed inside the powder nozzle. And that is the solution for this topic was now to remove the filter or to make the filter a little bit larger. This filter was only for to save the machine. So in general, our hint was to move that filter. And after the customer did that, they work perfectly. What I didn't mention, we have a vacuum in the chamber of around about 200 millibar. So 80 to 90% vacuum inside this chamber. And another topic was for cacao and milk. It's the same. We have here an pulsating vacuum. And then, what could be the topic? And then we said sources set up. We have an unfavorable T-piece here. We have one here, and a third one here, which just comes back to the process tank. Why it's unfavorable? Unfavorable means we get the 90 degree of the T-piece. That means we don't have the straight way. We have the 90 degree, and at this 90 degree, we have a pressure drop. or on the other side, we create back pressure to the system if you want to push something through it. And the next thing was when we end in the process tank, we have something like this piece here, which is pushed against the wall, so that we come here with 30 to 40 cubic meters per hour of milk, which is sprayed directly to the wall. And that creates also a back pressure. So we give our customers a hint, hey, connect the machine directly to your process tank, maybe over this valve, over this pipe here, and you will get a fine powder suction in. The customer did that, and we get also the response that it works now fine. What we also said as a hint is if we can create a return, do it under level, also under the liquid level, so that you don't have spray it overall in your process tank and you have a fine circle without any impurities on the wall. And what also important is that the quantity DS should be the lowest point in your total in your whole setup, like every pump. Now here I show you what I mean again with the unfavorable T-freezes. This is not what we want to have. This is okay. If you need a bypass or something like that, just put it in the 90 degree, and for the normal way, choose the straight way through the piece, T-piece. Yeah, one special topic is for battery, especially if you want to mix under high viscosity, and the shear rate should be not too high, and you want to avoid centrifuge effects, like for example in the battery field is you mix carbon, you have your metals have to be mixed, and you have a binder. So all three powders with a different density. And if you work with a normal dispersion machine, you create high shear rates, and then you have a centrifuge effect inside. And to avoid that, we have created a special type of rotor-stator system, which I don't mention here in this talk, but just in general, with our machine, we can achieve the same results with like a planetary mixer, like you see here for a raster microscope image. We achieve the same results in a way shorter time. A planetary mixer needs for this result around about 2 to 3 hours minimum, and we did it in just 1 minute, for example. Yeah, as an outlook, what is important, and yeah, avoid filters, T-pieces, and heat exchangers in the dispersion loop. Of course, check every time the boiling point and the vapor pressure of the solvent. For example, if you work with water, also 80 degrees is the maximum temperature during the powder induction. Yeah, choose the right pipe size, which is related to the machine and with what we suggest to the customers or to you. Yeah, think about the viscosity and also from the start to the end of the product. And what is very important, we need cooperation between the system integrators and the suppliers, so that everyone talk together and think about what is important for the process in general to get out the best result for everyone. Yeah, and that I would thank you for your attention, and we look forward to working together.
Thank you very much. Then you are also free to join and ask your questions over the F&A button, as we have it by our last speakers. So please use the F&A button at the bottom of your screen, or if you're joining via LinkedIn, the comment section. So I will give you a few moments that you can type in your questions. And also, no, I check. So maybe one first question. So how do I determine the correct amount of powder to add to the liquid?
Yeah, for the powder side, we have to check at first the bulk density and the flowability of the powder. That means that have to be considered and have to check. And then we can give the proposals what we have to do if we suck in very fast, like I showed for chalk. And if you talk about binders like xanthan or cellulose, then we have to reduce the suction speed, and the reducing is taken by reducing the pipe diameter on the powder side. This is the easiest way how you control the powder suction rate.
Okay, thank you for answering. So I wait that you can also type in your questions if you have some. One second question. So, how time-consuming is the cleaning of the systems?
Cleaning depends on the customer. Of course, in the food industry, it's a little bit different, maybe related to the pharmaceutical industry. But in general, the machine is sippable, and you can also work with your normal cleaning procedure, like you do it for your pumps and anything else you have in your system. So it's no special treatment needed, the treatment is related to the normal cleaning procedure. That's a huge advantage.
Thank you. So, if you don't have questions now, but afterwards, then you are free to ask your questions to pautek-technofarm@nürnbergmesse.de or directly to Mr. Holger Becker. So you see also the email address from him at the presentation. So feel free to ask then the question afterwards. So I will then thank you again, Mr. Holger Becker, and also our other speakers from today. So big thanks to Markel, Tim, and Holger. So we're now at the end of our talk. And I want to also thank you as participants from our virtual talk that you are joining. And the upcoming dates of our next virtual talks can be found on our website at www.pautek-technofarm.com/events-program. Or also on our social media platform, LinkedIn. There we will be informed very good. So stay tuned and feel free to join again. And we are very much looking now forward to Pautek Technofarm, Fachpack and Partec in September from 23 to 25 September 2025 this year. So also we're hoping that you will join us there and we can see you in person live. So then have a nice day and I hope to see you soon. Bye bye.